Hello students, I have come with another video on galvanic cell. Galvanic cell is very important both for competitive as well as for board level. The concept behind galvanic cell, I will try to explore all the concept which is required. First of all, galvanic cell is a part of device where chemical energy converted to electrical energy. In this case, there is no source of current. The chemical reaction takes place, converted to chemical energy, converted to electrical energy. Now, a galvanic cell consists of the following parts. It consists of two half cells. Left half cell is anode, where oxidation takes place. It can be represented by, suppose A is a metal which is dipped into solution containing its own ion and converted to An+. As for example, copper metal dipped into copper sulfate solution, 1 molar solution. When a metal dipped into its solution, a potential is developed in contact with the metal with its solution. It is known as the half cell potential. Half cell potential can be oxidation, can be reduction, depending upon the other half cell to which it is connected. So left half cell is known as anode, where oxidation takes place. In this case, it is the negative part. Now, number 1, number 2, right half cell is known as cathode. Where reduction takes place. As for example, suppose copper sulfate, when converted to copper, in this case charge of the copper is 2+, it converted to Cu, it takes up 2 electron. Now, a galvanic cell consists of two parts. In one half cell oxidation takes place, in another half cell reduction takes place. Suppose I have taken a zinc sulfate solution, in which zinc metal is dipped. Then we have copper sulfate solution. Where copper metal is dipped. When a metal dipped into its solution, its potential is developed in contact with the metal with its solution, and a potential is developed that is known as the single electrode potential. When these two are connected, galvanometer get deflected. That means chemical energy converted to electrical energy. This is negative, this is positive. These two are connected by means of a salt bridge to obtain continuous current. Salt bridge contain salt of strong electrolyte. Now, what is the function of salt bridge? Salt bridge maintain electroneutrality on the two electrodes so as to obtain continuous current. It is a negative part, it is a positive part. It doesn't allow any accumulation of charge near the electrode such that we obtain continuous current. Now, what will be the standard EMF when the two half cells are connected? This can be done as follows. Standard EMF is denoted by E0. In the left half cell it is oxidation, it is written as E naught OX means oxidation left plus E naught reduction right. This is most important part. In order to obtain continuous current, E naught should be positive. To obtain continuous current, when E naught is equal to 0, system at equilibrium. When E naught is negative, no reaction takes place. These are the basic things. Now, I've told you in this case, when I take the case of zinc and copper, in the case of left it was zinc, in this case oxidation takes place. In case of copper, it was the reduction takes place. Oxidation potential of zinc electrode, zinc to Zn2 plus, it is given in the book, it is 0.76 volt. And it is 0.34 volt. It is 1.01 volt. 1.10 volt. As it is positive, so reaction takes place. Now, standard oxidation, this is very, very important part, what I am discussing now. Standard oxidation and standard reduction. Potential are equal in magnitude. But opposite in sign. That means E naught Zn to Zn2 plus can be written as minus E naught Zn2 plus to Zn. It is the case of oxidation, it is the case of reduction. Oxidation, reduction are equal in magnitude but opposite in sign. If oxidation is positive, reduction potential has to be negative and vice versa. Generally, we follow the conception E naught standard EMF of the cell equals to E naught reduction right minus E naught reduction left. Because without writing oxidation at left and reduction at right, we follow the convention reduction at right and reduction at left. Suppose I have given this potential as follows: A naught A2 plus to A, E naught value is given as minus 0.12 volt, and B2 B plus, E naught is given as, let it be E naught 1, it is E naught 2. In this case it is given as 0.04 volt. In this case, in one case it is given the oxidation potential, in another case it is the given as reduction. In one case it is the reduction potential A naught to A involve addition of 2 electron, in this case B2 B plus involve loss of 1 electron. Now when I find out the standard EMF is intrinsic property, it is irrespective of the number of electron takes place during oxidation reduction. In order to find standard EMF, what should I do? I will follow the convention. E naught is equal to E naught reduction at right minus E naught reduction at left. How should I come to know where oxidation, where reduction takes place? In one case, first case, it is given as reduction potential. Second case is given as oxidation potential. What shall I do? What I will do first? I will first find the reduction potential of both the half cell. The first half cell reduction is already given. For the second half cell, reduction potential will be what? E naught B plus to B. The reduction potential would be equal to oxidation reduction potential. I told you are equal in magnitude and opposite in sign, as it is given as 0.04 volt, so it will be minus 0.04 volt. So reduction potential of the two half cell are, in one case it is E01, that is A2 plus 2A. A2 plus 2A is minus 0.12 volt. Let us mark with red color. In one case, E naught A2 plus 2A is equal to minus 0.12 volt. In another case, it is minus 0.04 volt. Out of the two half cell, which is more? Less the negative value, more will be its value. So in this case, B plus to B is more than A2 plus to A. In this case, not only magnitude but sign is also taken into consideration. So due to higher reduction potential, it will act as cathode, so it will be at right, and due to lower reduction potential, it will be anode, it will be on the left. So EMF of the cell can be calculated as follows. I have already discussed E naught A2 plus to A minus 0.12 volt, E naught B plus to B minus 0.04 volt. For finding standard reduction potential, what should I do? Reduction at right, I will use the formula. In this case, what it will be? Minus 0.04. Due to higher reduction potential, it will act as cathode, and due to lower reduction potential, it will act as anode. .08 volt. As standard EMF is positive, hence reaction will be spontaneous. Representation of the galvanic cell, it will be on the, due to lower reduction potential, it will be on the left, it will be on the right. So representation of galvanic cell will be what? A to A2 plus, double stroke called salt bridge, B plus to B. Okay. Now, metals are known as reducing agent. Less the reduction potential, it will be the stronger reducing agent. Suppose I have given a case where is given reduction potential of NO3 minus in aqueous solution. Is given by reduction potential of NO3 minus in aqueous solution is given by 0.96 volt. In this case, the reduction potential of three metals is given as follows. First of all, Fe3 plus to Fe minus 0.04 volt. Minus 0.04 volt. Next case, it is given as Hg2 plus to Hg 0.86 volt. third case is given as another case. In this case it is given as, all of them are standard reduction potential E naught. Curl E means reduction potential. E naught A3 plus AU 3 plus 2 AU is equal to 1.40 volt. Now the question is, which of the two metal will be oxidized by NO3 minus in aqueous solution? Now it is a redox reaction. If NO3 plus reduced, other will be oxidized. Reduction potential of NO3 in aqueous solution is 0.96 volt. I will check up whose reduction potential is less than that. In case 1 and case 2, the reduction potential are less than 0.96 volt. So hence Fe and Hg having lower reduction potential than NO3 plus, NO3 minus, very sorry to say, will be oxidized by NO3 minus in aqueous solution. As reduction potential of AU3 plus to AU is more than reduction potential of NO3 minus, hence AU will not be oxidized to AU3 plus, but other two will be oxidized. In this way, out of a pair of half cell, first I will look at whose reduction potential is more. The part whose reduction potential is more will be reduced, and the other part whose reduction potential is less will be oxidized, because oxidation reduction takes place simultaneously. Next point, E naught is intensive property. Intensive property means what I want to tell. Suppose in this case, NO3 minus plus E plus 2 plus E, suppose NO2 minus. It has the oxidation number of plus 5, it has the oxidation number of 3, so it involves addition of 2 electrons. In this case, AU 3 electrons are transferred. AU won't be oxidized because reduction potential is more than that. Forget about AU. Think of the case of your Fe. Think of the case of your Fe. Fe having reduction potential of what? Fe oxidized to Fe3 plus. Fe oxidized to Fe3 plus will have a value of in this case, E naught value is 0.96 volt. Reduction potential was minus 0.04. Oxidation potential will be what? I told you reduction and oxidation are equal in magnitude and opposite in sign. Will be minus 0.04 volt. Okay. So reduction was negative. So oxidation will be positive. On adding these two, in this case we don't consider the number of electrons transferred. In this case 3 electrons are transferred. So we have no need to consider, we have no need to make oxidation number of electron lost and gains are same to find standard EMF of the cell. Standard EMF will be what? In this case reduction at right, minus E naught Fe3 plus to Fe. It was 0.96 minus the reduction potential was what? 0.04. So in this case it is amount to 0.92 volt, which is positive. Hence the reaction is spontaneous. In this way, when the two half cell is given, how to judge where oxidation reduction takes place, we can do this way. Now, when the concentration of the half cell was other than 1 molar, in such case, EMF can be determined using Nernst equation. The logic of the Nernst equation is as follows. I am explaining these things to you. Suppose we have zinc. We have taken zinc sulfate. It is a negative part. Salt bridge, copper sulfate and copper. In this case, oxidation takes place. So, cell reaction. First, I'll write down the cell reaction. Suppose it is 0.1 molar. It is given as 0.2 molar. Cell reaction will be zinc loses 2 electron forming Zn2 plus. On the other hand, Cu2 plus takes up 2 electron forming copper. On adding these two, in this case we have to make number of electrons given and taken and same to find equilibrium constant. In this case 2 electrons are lost, 2 electrons are gained. So these two cancels, is gives you Zn plus Cu2 plus, gives you Zn2 plus Cu. Equilibrium constant will be product by reactant. In this case we never consider the solid one, its activity taken to be 1. So in this case it will be Zn2 plus, in this case it will be Cu2 plus. Zn2 plus concentration is 0.1, Cu is 0.2. So K is equal to 1 by 2, that is 0.5. Now Nernst equation is E, desired EMF. When the concentration is other than 1 molar, the EMF won't be standard EMF. In this case, EMF can be determined using Nernst equation. To find standard EMF, solution should be 1 molar and temperature should be maintained at 25 degrees Celsius when the metal dipped into its solution containing its own ion. Using Nernst equation, E is equals to E naught minus 2.303 RT by NF. N means number of electron transfer, F is the Faraday, log K, K is the equilibrium constant. R value I have taken as 8.314, T as 298 Kelvin, F as 96500. The whole thing become 0.059. E equals to E naught minus 0.059 by N log K. N is the number of electron transfer, K is the equilibrium constant. In this case, I can determine the EMF of the cell. Now, suppose we want to find out the equilibrium constant of a cell. How I can find out the equilibrium constant? Now see, at equilibrium, I told you EMF should be 0. At equilibrium, what we have? Delta G naught equal to minus NF E naught. Delta G naught is equal to minus NF E naught. N is the number of electron transfer, F is the Faraday, E naught is the standard EMF. On replacing the value, I can determine the standard Gibbs free energy. Standard Gibbs free energy can be calculated using this value. N is the number of electron transfer, F is the Faraday, E naught is the standard EMF. Delta G naught means Gibbs free energy. At equilibrium. N number of electron transfer, F is a Faraday, having the value 96500 Coulomb. Okay, E naught is the standard EMF. Suppose for this reaction, E naught is given as, for the reaction Zn to Zn2 plus, double stroke, Cu2 plus to Cu, E naught is given as 1.10 volt. If they ask you delta G naught, how should I find out? Delta G naught is equal to minus N F E naught. N is 2 minus 2 into 96500 into 1.10. It will be volt coulomb or joules. Now standard gives free energy with standard EMF. Now if I want to find out equilibrium constant, how I can do that, that part I will tell you. Delta G naught is equal to, minus RT ln K. ln means 2.303 log K. So if I equate these two, R means gas constant, T is the temperature, K is the equilibrium constant. K equals to, or E naught is equal to RT by NF. ln means 2.303 log K. The whole thing equals to 0.059. So E naught is equal to 0.059 by N. N means number of electron transfer, log K. K is the equilibrium constant. In this way, I can determine the equilibrium constant knowing the standard EMF. It is a long topics. Let us up to this. Next day I should do one more part of it.